Hello, welcome to today's lecture on kernel methods. We will be discussing the topics of support vector machines, that is SVM, and the kernel methods, or the part called kernelization, which is nothing but basically projecting your data points onto a higher dimension so that they become separable. Right, so let's start. Right. So when we talk about SVMs come under linear classifiers, or they can be nonlinear classifiers as well. So let's talk about a linear classification problem. All right. So let's say we have two sets of data points and we want to linearly classify them. Right. For that, there are many different linear classifiers available, and we want to find the one that best fits or best generalizes these set of data points, right? And that vector or that decision boundary, this is called the decision boundary, right? This creates the maximum margin between the two sets of data points, right? So like we can train our weights so as to get the perfect decision boundary, which is given as w dot x is equals to t, right? So in order to do that, we use support vector machines, and support vector machines get you the best decision boundary that is possible, right? And we'll also discuss about the dual form while using support vector machines, which makes them really easy to use and really easy to classify. Right. So we've established the fact that support vector machines get you the best decision boundaries. Now let's see how we get that. Right. So let's say we have these two sets of data points, right, which are distributed on a two-dimensional plane. Right. So these are two sets of data points. Right. So now, as you see, we get a decision boundary. Right. We get a decision boundary, or maximum margin hyperplane. This is also called maximum margin hyperplane, right? And it is defined by the equation w dot x is equals to t, right? Now, this decision boundary, or this maximum margin hyperplane, is built with the help of support vectors, which are basically the points that lie at the minimum distance from this decision boundary, right? So we want to maximize a margin by plotting support vectors which are at the minimum distance from the decision boundary, right? So we take these as our supporting vectors. Let's say even this is a supporting vector and the line crosses from it. So we uses these 4 points as our support vectors in order to build our decision boundary, right? And these support vectors are defined as x is equals to t plus m, and w dot x is equals to t minus m, right? So if you want to visualize this in the form of vectors, this would be something of sort, we have w here, right? um, Similarly, this is the x vectors, right? So this would be given as t minus m upon mod of w, the length of this vector. Similarly, this vector would be given as t plus m by mod w, right? This is the length of this vector. So we can find the length of our margin as well by subtracting these two, which results in 2m by mod w, right? So 2m by mod w gives us the length of the margin. Okay. So basically the support vector machine finds the decision boundary that maximizes m by mod w, because we want to increase this distance, because the more separated our data points are, the bigger the margin is, so better the generalization is, right? So we just want to maximize our m by mod w. Now we see that as we want to maximize our m by mod w, right? And just for the it's customary to choose our m as equals to 1. Okay, so if we want to maximize the margin, therefore if we take m as equals to 1, we would want to maximize our 1 by mod w, right? If we want to maximize this function, we would need to, if we want to maximize this function, right, we would need to minimize our mod w, because the smaller the mod w is, the bigger the value of 1 by mod w is, right? So to make it mathematically convenient, what we do is, let's say our h of x is an increasing function, right, where we take hx as x square by 2, right? So if we want to, and let's say this is called f of x, that is mod w. So if we want to minimize our f of x, or uh, we would have to minimize our h of f of x also, because h is an increasing function, right? So this would mean we would have to minimize our w square by 2, right? And that is what's explained on our slide 29, where it says that this leads to a quadratic constraint optimization problem, because we, for mathematical convenience, we converted our mod w to mod w square by 2, and we try and reduce this. All right, so as we see, um, like we built our svm, right, something of this sort. This is a support vector, this is our decision boundary, another support vector, and we have negative classes here, and we have taken our m as equals to 1, right? So according to our initial equation of the decision boundary or the support vectors that we took, that was equals to w dot x is equals to threshold, this was w dot x is equals to t plus m, and this was w dot x is equals to t minus m, right? As we have taken the m value as equals to 1, we write, instead of t plus 1, the equation of our separating hyperplanes become t plus 1 and t minus 1, right? So that is why, so let's say this is class 1, this is class 2, this gives us the equation of our two decision boundaries, right? So that is why it takes care of our like it says that it is subjected to yi wi or xi into w minus t greater than equal to 1. Now as you can see, this is like pretty intuitive, and this sums up all our three equations in one. Why? See, you see the first equation, anything lying on this line or above would have, or on this line on the support vector would have w dot x minus t is equals to 1, right? Similarly, anything lying on this class, on this line, on this support vector or below would have w dot x minus t is equals to minus 1, right? For class 1, we take yi is equals to plus 1, and class 2, we are taking yi is equals to minus 1, as it's two class separating problem. So as you can see, if it's correctly classified, then w dot x minus t is equals to plus 1, and our yi is equals to plus 1, right? So this would make equal to 1, right? Or anything greater than that would be greater than plus 1, because anything lying above this line would have an equation w dot x minus t greater than 1. Similarly, anything lying below this line would have an equation w dot x minus t less than minus 1, right? So if it's correctly classified, that is like if its label is minus 1 and it is classified it as it is classifying it as -1, then our subjected equation again becomes greater than equal to 1, right? Therefore, we have succinctly put both the conditions into just one, saying that the equation is subjected to yi xi minus t greater than equal to 1. For any correctly classified sample, this would hold true. All right, so let's continue. So as it was shown in the lecture that it is easier to consider the dual problem where we'd have to find argmax minus half sigma alpha I alpha j yi yj xi xj subjected to sigma alpha I yi equals to 0. I'll show you how we derive all of these. So before starting with the dual problem, let's introduce another variable, that is alpha I, where I stands for ith data point, and the value of alpha depends on the classification of the ith data point, right? So if our data point is correctly classified, then we leave alpha as it is. But if it's wrongly classified, we add, let's say, that would mean yi w dot xi minus t is less than 1, right? That is, it's incorrectly classified, that it was either positive sample classified as negative or a negative sample classified as positive. What we do is we increase the value of alpha by 1, right? So you can define alpha by alpha is a multiplier that is incremented by 1 every time the data point is misclassified, right? So that clears our alpha. If we know what alpha means, we can write our um, optimization problem in terms of Lagrange function. Lagrange function is given as Wt, as there are n data points, there are going to be n alphas, right? Half W square minus sigma I equals to 1 to n alpha I. This is for all the wrongly classified samples. Alpha I yi w dot xi minus t minus 1. Okay, so this is just basically this would tell you it's +1 or -1, and it will tell you the difference between it. Okay, so we try and solve this now. So this was just because if it's correctly classified, this whole term would become 0. If it's incorrectly classified, this whole term would exist, right? So proceeding forward, we split this up. If we split this up, we get half mod w square minus sigma of alpha I yi w xi, right? I goes from 1 to n, plus sigma I goes from 1 to n alpha I yi t minus sigma alpha I, right? Now this is 1 by 2 dot product of w. Taking w out, we get sigma alpha I yi xi plus sigma, taking t out, alpha I yi minus sigma alpha I, right? So as we know, this is a constraint problem, and it depends on w and t. We differentiate our Lagrangian formula with respect to w and t, getting if we take with respect to t, what we'll be left with, this becomes 0, this becomes 0. We are only left with sigma of alpha I yi equating it to 0. And if we differentiate it with respect to w, we would get sigma alpha I yi xi, right? Minus w minus, sorry, w minus, because this term becomes w. This term, as w is multiplied by sigma alpha yi xi, it becomes minus sigma alpha yi xi, equating it to 0. we get our W is equals to sigma alpha I yi xi. Therefore, this proves that every time a sample is misclassified, we add alpha I yi xi to our weight vector, updating the weight, hence updating our decision boundary, hence creating a larger margin. Okay, so as this is the same expression that we derived for the perceptrons, right? So now what we need to do is we have found our W. Now replace this value of W back here. Okay, right. So replacing the value of W back into our Lagrangian variable, we get alpha 1 till alpha n is equals to minus half sigma alpha I yi xi sigma alpha I yi xi plus sigma alpha I, right? So expanding this, we get sigma I goes from 1, j goes from 1 to n. This becomes alpha I alpha j yj xi xj plus sigma alpha I. I know it looks intimidating, but it's really simple. We'll take up an example and it will all be clearer to you. So this gives us basically the SVM in dual form, right? It's really easy to simplify and solve this, and it is subjected to alpha i's are greater than equal to 0 and sigma of alpha I yi is equals to 0, because this is what we found when we differentiated it with respect to t, right? Okay, so let's take up a toy data set and I'll try to explain what gram matrices are and how we use them in our SVM in dual form. Okay, so as it is given in our question 2 in our tutorial, that we have 3 points represented by this vector x, right? And we have y labels associated with each of these points, that is +1, and -1. So if you visualize this, this is basically, if you take points 1, 3, the first point is here, second is 2, 1, second point is here, and the third point is 0, 1, that is here, right? And it is given that these 2 points are considered as +1s and this point is in negative class. So we want to build a decision boundary that basically differentiates between these two classes. And we can build this decision boundary through SVM in dual form. Okay, now in order to do that, first we would need to find x dash. X dash is nothing but x into y, x dot y. That would give us 1, 3, 2, 1, 0, -1. Right. Once you've found our x dash, our gram matrix is defined as x dash transpose. Right. So in order to find a gram matrix, we need to multiply 1, 3, 2, 1, 0, -1 with 1, 2, 0, right? 1, 3, 2, 1, and 0, -1. If we multiply both of these two matrices, we are left with, I'll just do the calculations. The first one is 10, 5, -3, 5, 5, -1, -3, -1, and 1. Right. So this gives us our gram matrix. So if you look closely, what we are doing, x dash is x dot y. So this is x dot y transpose, right? Which is basically finding out yi yj xi xj, right? So now we have built a gram matrix that brings us to our third step. Now the third step would be, once this gram matrix is built, we need to multiply it with alpha I alpha j. So when we multiply it with alpha I, alpha j, right? So that would be this. That would result in the dual optimization problem, which would give us argmax alpha 1, alpha 2, and alpha 3 minus half. Um, this would be 10 alpha 1 square plus 5 alpha 1 alpha 2 minus 3 alpha 1 alpha 3 plus 5 alpha 2 alpha 1 plus 5 alpha 1 alpha 2 square, my bad, alpha 2 square, then minus alpha 2 alpha 3 minus 3 alpha 3 alpha 1 minus alpha 3 alpha 2 and plus alpha 3 alpha 1. Adding all of these together, we are left with, oh, I forgot, this is the first term plus sigma of alpha I. So that would be alpha 1 plus alpha 2 plus alpha 3, right? Because this was what? Um, double sigma of alpha I, alpha j, yj, xj. And this is alpha sigma of alpha I. Adding these two together, we'll get our SVM in dual form, right? So this would be alpha 1, alpha 2, alpha 3 minus half 10 alpha 1 square plus 10 alpha 1 alpha 2 minus 6 alpha 1 alpha 3 plus 5 alpha 2 square minus 2 alpha 2 alpha 3 plus alpha 3 square plus alpha 1 plus alpha 2 plus alpha 3, right? So it's clear till this step. Now proceeding forward, this whole system of equation, it's subjected to alpha I is greater than equal to 0, right? And as our y i's are plus 1 and minus 1, this would lead to alpha 1 plus alpha 2 plus minus alpha 3 is equals to 0. Why? Because we had the condition where alpha I yi is equals to 0, right? The system of equations were subjected to alpha I is greater than 0 and sigma of alpha I yi is equals to 0. Doing that, we get this particular equation. I will just write it again. So sigma of alpha I yi becomes alpha 1 plus alpha 2 minus alpha 3, which should be equal to 0. This leads to alpha 3 is equals to alpha 1 plus alpha 2, right? Replacing the value of alpha 3 back in this system of equations, right? Replacing alpha 3 by alpha 1 plus alpha 2, we get left with, I'll just write it down directly. You guys can do it on a copy, pen and paper. So you get argmax alpha 1, alpha 2, alpha 3. It's minus half 5 alpha 1 square plus 4 alpha 1 alpha 2 plus 4 alpha 2 square plus twice of alpha 1 plus alpha 2, right? So this makes us our, gives us our first equation. So now as you can see that this equation is just dependent on alpha 1 and alpha 2, right? So what we need to do is we need to differentiate this equation with respect to alpha 1 and alpha 2, equate them to 0 and find the values of our alphas respectively. Okay, so now differentiating it with respect to alpha 1, what do we get? We get minus 5 alpha 1, right? Minus 2 alpha 2 plus 2, and differentiating it with respect to alpha 2, we get minus 2 alpha 1 minus 4 alpha 2 plus 2. Now equating both of these equations to 0, we have two variables, two equations, right? And we solve for alpha 1 and alpha 2, right? Hence solving these two equations, we get alpha 1 as 1 by 4 or alpha 2 as 3 by 8, right? And we know that alpha 1 plus alpha 2 is equals to alpha 3, right? So this gives us alpha 3 is equals to 5 by 8, right? So now we have found our values of alphas, right? Now we can proceed to find our value of t, w, the size of our margin, right? So if you remember from the slides, we know that our w is given as sigma of alpha I yi xi, right? We have our values of alphas, we have our values of y, that was plus 1 and minus 1. Similarly, we have our value of x's. What were our values? X's were given as 1 3, 2 1 and 0 1, right? So using these values, the value of alphas, the value of y and the value of x, we can now proceed to find our value of w. Now how do we do that? This is 1 by 4 plus 1 into x1, right? Plus 3 by 8 to plus 1 into x2 plus 5 by 8 into minus 1 into x3, right? So this is equal to 1 by 4. X1 is 1 comma 3. Our x2 is 2 comma 1 and our x3 is, sorry, this is negative 5 by 8 0 1, right? Solving this, we get our w as 1 comma 1 by 2, right? So we have found our value of w. Once we have found our value of w, we can find the value of our margin, right? Our margin was 1 by mod w, right? So this would be equals to 1 upon root of 1 square plus half squared, right? Similarly, you can find the value of t. How you can find the value of t? You can replace any of these values of w, y and x in order to find t, because the original equation was subjected to yi wxi minus t is equals to 1, right? Now our yi, let's take y2 w dot x2 minus t is equals to 1, right? Our y2 is plus 1, right? Our w is 1 comma 1 by 2. Our x2 is 1 comma 3, right? Subtracting t is equals to 1. Therefore, this gives us the value of t as 3 by 2. So we have found our values of w, we have found our values of alpha, and we have found our values of t. So that gives us our decision boundary. The perfect decision boundary, that gives us the maximum margin. One important thing to remember is the values of alpha, that is alpha 1, alpha 2 and alpha 3 tells you the importance of the data points, right? The higher the alpha, the more important the data point. So that brings us to our next topic of kernel and kernelization, right? So what is a kernel? Kernel is a function, is a similarity function that basically corresponds to a dot product in some expanded feature space, right? So this would be defined as, let's say we have 2 points x and x dash. A kernel can be defined as the dot uh, product projected or expanded to a new feature space that is of order q, right? Right. So for example, let's take two data points, x1 that is defined as x1 by 1 and x2 that is defined by 2 points x2 and y2, right? These are two data points. Now consider a non-linear mapping such that x and y are projected to x square comma y square comma root 2 xy. Okay, so let's take a non-linear mapping such that xy is projected to x square, y square, and root 2 xy. So we would need to check that if it's a valid kernel or not. We need to project these points to the new feature space, right? So to project the points to new feature space, we find x1 dash, that is given as x1 square plus y1 square, sorry, x1 square comma y1 square comma root 2 x1 y1, right? This is the new feature space. It's three-dimensional feature space. Okay, because there are three axes in this. Similarly, we find x2 dash. X2 dash is given as x2 square y2 square and root 2 x2 y2, right? So to check if it's a valid kernel, it should be a dot product of both of these. So taking a dot product of x1 dash dot x2 dash, right? What do we get? Taking the dot product of both the 2 points, we get x1 square x2 square plus y1 square y2 square plus 2x1 y1 x2 y2, right? Which is similar to x1 x2 plus y1 y2 square, which is again similar to x1 dot x2 square, right? You see, as the new feature vectors x1 dash and x2 dash are a dot product of the old feature vectors projected to a new space, therefore this is a valid nonlinear kernel, right? So you see, just by squaring the dot product in the original space, we obtain the dot product in a new space, right? So if you want to basically know this visually, I'll just draw a diagram for you guys. So yeah, this would also mean that k x1 x2 is equals to x1 dot x2 square, right? Therefore this is a kernel, right? So if you want to visualize this, let's see, we have two non-linearly separable classes, right? Let's say we have crosses and we have circles, right? So let's build our two classes which are non-linearly separable, right? Something of this sort. As you can see, these two classes are non-linearly separable but not linearly separable, right? You can obviously build a decision boundary that separates these two data points, but building this decision boundary would be little complex because it is non-linear, right? Instead, what we can do is we can project these points, as these points currently are in a two-dimensional space. Using the kernel trick, we can project these points into a three-dimensional space, which through which they become linearly separable, right? What I mean to do is we change these points. If we use the kernelization trick and we project these points into a 3D space, so a 3D space would look something of this sort, right? Now you had your x's and you had your y's, o's. So now you see, as we have projected these points using a kernel phi on a three-dimensional plane, they were non-linearly separable in a two-dimensional plane, but as soon as they're projected in a three-dimensional plane, you see, these can be separated by using a linear hyperplane, right? So this is the use of kernelization, and it is a very useful thing and a very powerful technique in the machine learning area. So there are different types of kernels available, like there is RBF kernel, that is radial bias function. Then there is polynomial kernel. So if you want to Yeah. So RBF kernel, that is called the radial bias function kernel, right? It is defined by, if you put two dimensional points in this, it is defined by minus x dash square upon 2 sigma square, right? And the one we discussed before, it was called the polynomial kernel, right? That is given by x dot x dash minus or plus c raised to the power q. So let's understand the kernelization trick with the help of vectors, right? Or the feature representations, right? So let's say we have our 2 points x defined by x1, x2 and y as y1 and y2. Now, in addition to these 2 points, we are using the kernel kxy is equals to xy square, or polynomial kernel with c is equals to 0 and q is equals to 2. Okay, so in order to find x dot y square, we would need to take the dot product of the features y2 squared. This would give us, as it is a dot product, x1 y1 plus x2 y2 squared. This would lead to x1 y1 square plus x2 y2 squared plus twice x1 x2 y1 y2, right? This expression is similar to x1 square x2 square root 2 x1 x2 dot product with y1 square y2 square root 2 y1 and y2, right? Therefore, this kernel can be represented as phi of x dot product with phi of y, right? Where phi of x is equals to um, x1 square x2 square root 2 x1 x2. All right. So this would mean that using this kernel kxy equals to x dot y square, it would be equal to using this feature mapping in a new feature space, right? So that would mean just by taking the dot product of our 2 points and squaring it would lead to a new feature mapping in a new 3-dimensional space. So now let's take the example of our XOR. We know that our XOR function is non-linearly separable, right? Because you have okay, I'll mark from here positive, negative, negative and positive, right? So this is minus 1 comma 1, this is 1 comma minus 1, this is 1 comma 1 and this is minus 1 comma minus 1, right? So this is our XOR in x1 comma x2 space. Right. Now we'll show that how kernelization can affect our XOR function and make it linearly separable in a new feature space. So let's say we use a feature mapping phi of as it is consisting of 2 points x1 x2 is equals to 1 root 2 x1 root 2 x2 x1 square x2 square and root 2 x1 x2. Yes, we are projecting this 2-dimensional features into a 6-dimensional feature space when we are trying to solve our XOR. So using this feature mapping, let's try and describe our 4 points in 6-dimensional space, right? So we have, let's say, our first point 1 comma 1. Let's write as a transpose, so that because like we have a limitation of space. this would be equal to, this is 1. Yeah. So if you replace values of x1 and x2 in these, you will be get left with 1 comma root 2 comma root 2 comma 1 comma 1 comma root 2 transpose, because we're taking a transpose, right? Similarly, we take the second point. Uh, let's take -1 comma -1. That is also a negative class, right? This was a negative class. This would give us 1 comma minus root 2 comma minus root 2 comma 1 comma 1 comma root 2 transpose, right? Similarly, for the next 2 points, -1 comma 1 transpose and phi of 1 comma -1 transpose, we get left with 1 comma minus root 2 comma root 2 comma 1 comma 1 comma minus root 2 transpose. And the last one would be 1 comma root 2 comma minus root 2 comma 1 comma 1 comma minus root 2 transpose, right? So we have converted our feature space from 2-dimensional to 6-dimensional feature space. Now, as it is impossible to plot 6-dimensional features or 6-dimensional plane if I draw it by hand, let's just consider these 2 points, right? Just see the red marking. I'm just considering these 2 features out of these 6 features in the 6-dimensional feature space, right? So if you take these 2 features, this was negative, this was negative, this was for positive class, this was for positive class, right? And it was non-linearly separable initially. Now, if we just concentrate on these 2 points and try and draw them, right? Let's this is first, second point, third point and fourth point. So initially our points were, I just write down the names. Initially our points were this was -1 comma 1, so this was 3, this was fourth, this was first and this was second, right? So this was positive class, this was positive class, this was negative class and this was negative class. After we send it through a kernelization or a feature mapping, now considering just these 2 points, right, just these 2 points and mapping them on a 2-dimensional plane right now, because 6-dimensional plane is not viable right now, maybe in the future. So yeah, we try and draw this, right? So we have root 2 comma root 2. So root 2 comma root 2 would lie somewhere here, right? So this is the first point, right? Second point is minus root 2 comma root 2, right? Minus root 2 comma root 2. Minus root 2 comma root 2 would lie somewhere here, right? So if we like, let's take our origin here. This is root 2, this is root 2, this is minus root 2, right? And this is again minus root 2. So our second point is minus root 2 comma root 2. So this gives us our second point. I'll just mark these in blue so that it's visible. So this was our first point, root 2 comma root 2 or phi of 1 comma 1 transpose, right? This is our second point, that is minus root 2 comma root 2. If we go on to build our third point is minus root 2 minus root 2. This would lie somewhere here. And similarly, our fourth point would lie here. Now, as you know, the first and second points were of negative class. Third and fourth points were of positive class. So if we project these points on a 6-dimensional plane, you see these points become linearly separable, right? So this is the fundamental technique or the reason to use kernel tricks. This leads to a real simple solving of XOR function if it's projected to a six-dimensional plane. So while considering this, we have considered two features that are root 2 x1 and root 2 x1 x2. So this is basically root 2 x1 comma root 2 x1 x2 space. Okay, just because we are just considering just two samples or two points from our feature space. So now you must be wondering, okay, how did we get to using the six-dimensional feature space, right? So let's proceed forward. Okay, let's try and find out phi of x and phi of x dash. Like this is x dash is basically y, right? So you get 1 root 2 x1 root 2 x2 x1 square x2 square and root 2 x1 x2, right? And similarly for y dash or y, let's write it as y only. That'll be simpler in order to understand, right? Let's take this as y. So y would be 1 root 2 y1 root 2 y2 y1 square y2 square and root 2 y1 y2, right? Now if we take a dot product of these two, we'll be get left with 1 plus 2x1 y1 plus 2x2 y2 plus x1 square y1 square plus x2 square y2 square and twice x1 x2 y1 y2. Keep in mind that x is consisted of x1 x2 and y is made up of y1 and y2. These are two data points. Okay, so if we have this, if you look closely, this is nothing but 1 plus x dot y square, right? Hence this is a valid kernel. It's a polynomial kernel where c is equals to 1 and q is equals to 2. So if we use a polynomial kernel, we get a six-dimensional feature space that makes our XOR linearly separable. So this pretty much covers our SVM and kernelization. I'll see you next class.